Hello, everybody. This is Kazmiric. I am here. It's great to be with the Hungarian chapter of Isaca, to be working with you guys and to be participating in your annual conference. It's the second time I'm doing this, albeit virtually this time. The first time I was actually physically able to travel to Budapest. So it's a joy to be here. And I thank the chapter board and Greg and the leadership and everybody who's here listening. So let me do my quick share here. PowerPoint and share, and there we go. All right, I am here to talk about bleeding edge technology and the future of business, particularly for auditors. So there's three technologies I want to talk about: artificial intelligence, big data, and quantum computing. And these three technologies are very interesting to me, and I've spent a lot of time thinking about them, listening to very knowledgeable people talk about them. So first of all, just talk about who I am, what I do. I'm presently a professor, adjunct professor at Boston University, teaching IT governance and cybersecurity. I also have a one-man consultancy. I'm an accredited CISA, CRISC, CISM, Seagate trainer. I hold the CDP SE. I'm also an accredited CISSP trainer. I have an 85% pass rate on the people who take my trainings on the certification exams. So that's what I do. I like sailing. I like riding my bike. Both of these pictures were taken within the city limits of Istanbul. And if anybody has any questions about this presentation or anything else related to our profession, please send me an email. Feel free to call me. I'm on Instagram, Facebook, LinkedIn, my hashtag, or I should say, at Kaya Kazmiric together. That's also my Skype address if you want to call me. But again, feel free to initiate communication if you have any questions or comments about anything that I do or anything that we do. So first thing I want to talk about is AI, artificial intelligence. So what is artificial intelligence? How does it work? Artificial intelligence is a fairly complex thing. It's basically composed of two systems. The first thing that we need to be aware of, two sets of data, shall we say. The first is called a classifier. A classifier is the logical decision-making machine of AI. And what it does, what it's composed of, it takes an input, creates an output, which is a class label, and it includes a set of parameters that are how it defines the decision-making process. So it takes an input and it gives you a label, basically. Input, output, and there's a set of parameters that define how it takes decisions. The second part of AI is what's called a supervised training data set. Now there's unsupervised training, there's all kinds of other things, but primarily most of the AIs that I've seen use supervised training data sets. And what the training data set is composed of is basically inputs, outputs, and annotations about those outputs, which we call a target or a label, all right? So the main thing that I'm seeing now with AIs is everybody has their own classifier, but the training data set is what they use to get the data, to get the classifier to where it needs to be in terms of the decision-making process. So an example of this is I have a client, they do patent and trademark registrations in Turkey, and they use translation software called Trados. And they allow, the translators that they work with generally all have a licensed version of Trados. And when they send them translation work to do, they also send them what they call the translation memory, which is basically the training data set that is affiliated with that particular piece of translation, whether it's pharmaceutical, whether it's technology, IT, whatever the area is, there's a set of training data that tells the translation software how it needs to translate generally from English into Turkish. So, and there's also the way it needs to be filled into the forms and things like that. So the supervised training data set is what is shared with the translators so that they can get their classifier, their Trados software, to perform the translation correctly. And then the translators look at the translation, they review it to make sure it's accurate, they input their corrections into the supervised training data set, because again, it's supervised data. The system makes a translation, and the supervision are the translators who look at that and say whether it works properly or not. Okay, so the sharing the data set broadly for translation data sets is not an issue. Nobody cares. But in financial services, sharing training data sets is very sensitive because generally it includes deposit holder information. So in that case, in AI, we use something called federated learning. And federated learning is where the classifier training is done. Is it done in a distributed fashion? And the classifier parameter information is updated. So there's no sharing of training data in federated learning, but the parameter information for the classifier is what's shared. And the reason we do this, again, is because generally in financial services, nobody wants to share their deposit holder information, and data sets generally do include deposit holder information. Training data sets do include deposit holder information. So that's kind of the structure of AI, how it works in a very simple fashion. And again, if we want to get into classifier logic, Bayesian decision trees, and there's all kinds of real deep technical details that people with very large brains spend a lot of time thinking about. All right, so, but from an audit perspective, there's a decision engine called the classifier, and there's training data set that tells the classifier how it needs to work. That's all we really need to know, okay? And what the next thing we can think about is how might we compromise the AI, okay? So there's a couple things that can happen. If we take the training data, if we can access an organization's training data, say the training data that a bank used to train its interactive voice response system that deposit holders call in on and access their account information on, we can actually discover holes in the training data set so we can find ways of breaking into systems via holes in the training data. So there might be a simple question that we could ask a classifier that has been trained with training data that has a problem with it, like, how blue is the color blue? Who knows what that might create some weirdness within the classifier and give us data access. So that's an example, all right? So if we can get the training data, we can test it and we can find holes in it, or if we can compromise the training data, we can put a hole into our bad guys, not we, but the bad guys, if they access the training data, they can go into it and they can corrupt it. And from the corrupted training data, the classifier will make mistakes. Okay, by the same token, now training data in financial services generally held fairly securely. So the classifier parameters are the things that are shared. And the same thing is true if we can access the classifier. The classifier parameters, we can discover logical errors within the classifier logic, or if the bad guys choose to corrupt the classifier parameters, cause incorrect updates, then there can be logical errors implemented in the classifier decision-making process. And here is an example. When I was putting the slide deck together last week for this presentation, what did I get? The postman came by and he gave me a ticket, a speeding ticket, all right? Now in Istanbul, we have all the major thoroughfares have these big gates with cameras on them, these kind of that overhang the road. Basically it's places where the distance between the two cameras is known. There's a picture taken of the car entering the speed zone and leaving the speed zone, the time of entry, the time of exit. From down here, there's the formula. There's the distance between the two cameras, how long passed, how long it took me to get from one to the other, 108 seconds here. And again, multiply that times 3,600, means I was going about 100 kilometers per hour. Okay, well, the speed limit is 90 kilometers per hour. Guess what? So I got a ticket. Hey, 288 TL. That's the way it goes. Okay, so what does the AI do here when it takes a picture? There's an image processing AI. There's a classifier. First thing it does is it looks for the license plate. Boom. There's the license plate coming in and going out. Identifies the vehicle conclusively. All right. Where did it enter the speed zone? The picture down here in the second column here. Where did it leave? Which lane was I in? So I was in the left lane in both cases. How the picture was taken is pretty clear. Okay. The second thing the AI does is it identifies, it makes sure that it can see a driver here, enough so that we can identify it. Now, it just so happens that I wasn't driving the car. My driver was driving the car. I was in the passenger seat. The third thing it does is it covers the passenger seat. Now, why does it cover the passenger seat is a little more interesting. The first time the system went online, they just sent pictures of the car from the front. And there were many, many cases of these tickets coming to people's homes. The car owner's wife opens the letter, the envelope, sees a picture of their car with her husband driving it, and a woman that they don't know, or maybe a woman that they do know, sitting in the passenger seat. So all of a sudden, there were lots of questions being asked. Who is that person? Where are you going? Why are you driving together? Things like that. There were many, many divorces, and then the people that were getting divorced turned around and started suing the municipality. Hey, look, you took this picture of me without my permission, sent it to my home. Now I'm going through a divorce. You screwed up my life. I hate you. You owe me all this money. So the AI also looks at, makes sure that there's a big black thing around the passenger seat, so nobody can tell who's in the passenger seat. All right. So pretty straightforward, simple AI. How would a bad guy compromise this? So again, look at the license plate here, 58 ER 844, but look at the 8. There's something there. It's not really an 8, it's a 9. And it's been touched up to look like an 8 the same way. The E is not an E, it's actually an F. See? So here is a great case. The classifier understands what the license plate should be. It reads the license plate. But the classifier here, in this license plate, the classifier has not been, the training data is not detailed enough to show that the license plate, the tag, has been changed. So in fact, there's a compromise. This is a great example of compromising an AI. So we'll continue. Big data is the second thing I wanted to talk about. So data is air and data is everywhere, basically. Data is all around us, measured in terabytes, picobytes, even exabytes, okay? But to make sense of data, to turn it into value, we have to winnow it down to information, and then knowledge, and then wisdom. So gigabytes, megabytes, and then kilobytes is what it comes down to. So out of terabytes of data, to get wisdom or value, we really need to winnow it down into kilobytes. And the way we do that, I mean, going from unstructured data to structured data is the challenge, all right? That's really what we're talking about. We're taking a lot of data that's out there that's unstructured and turning it into information, and then knowledge, and then wisdom. So structuring it. Unstructured data is just content pretty much, and we use tools like Hadoop and MongoDB to kind of give it a little more organization. Structured data in our world is typically SQL. So, and it includes metadata and content. So whereas unstructured data is just content. There's no description that defines what that data is and what it means. So that's pretty much what big data is. Now, when we combine AI with big data, all of a sudden we have tools that automatically can turn unstructured data into structured data, which is great stuff, okay? Because that is golden. That makes a lot of money, okay? That can make us a lot of money. It can make anybody that can do this successfully a lot of money. So there's a lot of examples of this in our world today where this is being used. So investing in financial services is a big one. I have a dear friend whose son does program trading. He has an algorithm running, making trades, and he watches those algorithms to make sure they're working properly. Arbitrage is another huge business. Arbitrage is taking advantage of exchange rate differences in different markets and making buy-sell decisions based on those differing prices. So I know people that are doing this. They, Bitcoin, Ethereum, euros, dollars, yen, Swiss francs, and they're going back and forth along all these currencies on a daily basis. And they're using AI to kind of watch this. So, the margins on this are getting narrower and narrower as time goes on. If there's a big difference in the FX pricing from one market to the next, arbitrageurs will jump in there and kind of even it out all over the place. So media review, by the same token, a couple of years ago during the Barack Obama presidency, there's several Twitter feeds that report on the American Dow Jones on publicly held companies. So people, a lot of companies, when they're doing disclosures, public disclosures, they do it via a specific group of Twitter feeds. And one of these Twitter feeds was hacked. There was some news that came out about how there was a terrorist attack on the White House, and all of a sudden, all the automatic program trading softwares all were reading this Twitter feed, and they saw an attack on the White House, and they just started selling stocks. So a bunch of the stock prices started dropping. After a couple of minutes, people realized that this was not true. So the prices came up again. But what happened when they dropped, people bought in at a lower price, artificially lower price. And when the prices came back up again, they sold. So they made money. The bad guys made money. There's also a lot of work in AI in terms of climate prediction, real estate valuations. Again, I have a friend who's a farmer, and he uses some AI. Again, this is all stuff working on the cloud in America. He uses AI for weather processing, for predicting things like rain, precipitation, amount of cloud cover. And this has a huge impact on his decisions about using fertilizer, about when to water his fields. Again, water is fairly expensive. It's in a dry part of Turkey where his farm is. And, so he has to use electricity to pump water out of wells. So not having to pump water saves him a lot of money if he knows rain is coming, or if he knows there's a lot of cloud cover and he doesn't need to irrigate, then that's important stuff for him. So knowing when the weather is going to be the way it is very critical. One of my clients they use AI to track. I think there's a couple thousand different sources of electricity in Turkey in terms of power stations. There's wind, there's solar, there's hydroelectric, there's natural gas, there's coal. So there's there's a nuclear plant being built as well. So what my client does is they track more than 100 different line items for each power plant. Okay, things like wind speed, cloud cover, rain, ambient temperature, stuff like that. And from that, they can get a good idea of the supply of electricity. They have a they've historically watched the demand. So from their understanding of the availability, the supply of electricity and the demand, they take positions in terms of energy pricing. And they tell me they can make up to 10%. They can get a 10% margin on their energy positions based on their AI's ability to assess pricing moving forward. Logistics is a huge area for AI, particularly like airlines. I mean, imagine you are an airline. You have to carry, well, today actually in the COVID period, there's not a lot of airlines flying, but when they are flying, they have a certain number of passengers they have to carry from point A to point B. So using a plane that is filled to capacity is very positive, that can travel the distance that those people are flying. And how much fuel to use on that plane is another big one. So, and price of fuel and the various points. Of course, if you're carrying fuel, you have to use fuel to carry fuel. It's additional weight, so you have to enter the stuff. It becomes a fairly complex linear programming challenge, and AI helps airlines do economic routing and capacity use. So as well, AI is being used in pharmaceuticals. When pharmaceutical companies are looking at various molecules to use as medication, they need to assess those molecules and try to understand if they will actually be a successful drug. So there's a lot of work being done in AI now around assessing those and making sure they're working. And I talked about translation a moment ago. Okay, so quantum computing is another big technology. Quantum computing is basically based on something called a qubit. Okay, a qubit is a bit that can be either 1 or 0. Okay, so depending on whatever the solution to a problem is, it can be either 1 or 0, and it's kind of magic. I mean, ask it a question, and it answers. If it has enough qubits in it to answer the question, you get the answer like that. Kind of snaps out of it. It's really quite magical. And I wish I could say more about it, but it's a long and fairly complex thing. There's a lot of people with a lot of big brains working on this. So IBM's biggest quantum computer holds 65 qubits, which is fine. 127 qubit is coming in 2021, 433 qubit is coming in 2022, and a 1,000 qubit computer is coming in 2023. Now that's great. The preeminent form of encryption used today is PKI, public key encryption. TLS is based on PKI. TLS uses about a 2,000-bit RSA key for encryption. Now, if we have a 2,000 qubit quantum computer, what does that mean for PKI? It means it is no longer valid. And a 2000-bit quantum computer should be here in 5 years, according to the IBM timetable. So imagine in 5 years, TLS will no longer be valid. The answer to any encryption, to decrypt it, will be as easy as plugging in the ciphertext and the public key into a quantum computer, and boom, the private key will be there right away, provided we have a quantum computer that supports the number of bits of encryption being used in the key. All right, so yeah, 2048 bits for an RSA key is great, but guess what? I looked on my web when I was cruising the web, again, crafting this slide deck. The encryption that I was using for the TLS access was only 256 bits. So 256 bits means 2022, all right? In 2022, most of the encryption that we use is not going to work anymore. It will not be valid. It will be clear text very easily. So quantum computing has a huge impact on encryption as we use it today, all right? So the bad news is PKI is going away. Traditional encryption will be disrupted. The good news is private key encryption, where we use the same key to encrypt as we use to decrypt, will still work, provided the keys are longer than the number of qubits available in a quantum computer, all right? So what that means is we're gonna have really big private keys, all right? More than 10,000 bits, okay? And we're gonna have to use things like secure quantum key exchange, okay? Secure quantum key exchange works over a fiber optic connection. Basically, the sender and the receiver exchange the quantum key, and if there's a third party listening, then the exchange will be corrupted because there'll be somebody else on the line and it won't work. So that's the principle, that's the way it works. I understand that, well, I was giving a training to two members of a Deutsche Bank's board of directors last week, and I talked about this, and I said, I understand. I listened to a presentation from the head of security at KPN, which is the Dutch telecom operator, last year, and she was saying that there were a couple of Dutch banks experimenting with this, and I mentioned that in the presentation, and both of these board members, just their eyes kind of opened up and they got real quiet, their mouths just shut. So clearly the bank was doing something, in my mind, with that. I understand there's 2 Dutch banks doing experimentation with secure quantum key exchange, as well as a couple of Swiss banks doing work in this area. So again, and this will be a fundamental requirement. Within 5 years, there is no security unless you're using private keys for encryption, symmetric cryptography, as well as a secure way of exchanging those keys. So secure quantum key exchange is a good way to do that, all right? But PKI, TLS, secure shell will be disrupted. It's coming. 2-3 years, it's going away. PKI will disappear. That's my prediction, all right? It might be 4 years, but it might be 1 or 2 years. So you never know. We'll have to see what's going to happen. Thank you very much for letting me speak to you. I'm going to be available for questions. And again, thank you to the Budapest chapter for allowing me to be here.